Hey, this is Avi Gutman with another Ask Me Anything event brought to you by quantreasoning.com. I invite you to join me live next time. We do this every Saturday at 11 a.m. Eastern, and you can attend for free by starting your free trial at quantreasoning.com. So I think we're going to have a really interesting takeaway from this question that will be applicable to many different data sufficiency geometry questions. It's really almost across the board, the takeaway that we're about to see here. So first of all, it's a value question. They're asking for the value of x. And we have our right triangle, right? We do know one of the angles. The RPT is 90 degrees. And they want the value of x. Now, of course, without statements, I couldn't possibly answer this question. And the statements seem somewhat symmetrical, like they're giving very similar kind of information. So I would start with statement 1. And here's the trick for data sufficiency geometry specifically. You want to try to visualize, to imagine the degrees of freedom that the statements allow for. Or if you look at the other side of that coin, what are the constraints that each statement is giving us? So focusing just on statement 1 at first, if we're told that QR is equal to RS, those two sides are equal, that means that if I want to move the segment QS, I have to move it parallel to where it is currently. Because if I change the angle of segment QS, that would go against what statement 1 is telling us. So our degree of freedom, if you will, is we can move QS up or down, but it has to stay parallel. So I tried to make a little animation here. Actually, it was my wife who did it, so we can thank her. See, I moved QS. It's still parallel to where it was, but look what happened to angle X. So angle X was this angle. And it seems to me that if I move it there, it's now a bigger angle than it was. And if we move it to the other side, like make it the other extreme, look how tiny angle X is now. So if you can visualize that in your head, just kind of visualizing moving QS up or down parallel to where it was, you can kind of see in your mind's eye that the angle, the size of the angle X keeps changing. And that's enough to prove that statement 1 is not sufficient on its own, because if statement 1 still allows for all these different possible values of x, then it's not sufficient on its own, and we can go ahead and eliminate the statements that claim that it is. But do you see how if you explore the degree of freedom that the statement allows for, you can kind of prove insufficiency in geometry just by visualizing it? Do you see how that strategy can work? Let me just show you that animation one more time. Let's just look at this. Like from here, look at the size of x. And look at the size of x now. And I'm following the rules, right? I'm looking at what statement 1 tells me. And as long as QS moves parallel to where it was, we're following the statement, we're following the rule, and yet we're getting very different possible values for x. So that's probably my favorite strategy for proving insufficiency in geometry data sufficiency. Let's see if we can do that for statement 2 as well. So we're back to the starting point. This is what the diagram looks like. And if we're just focusing on statement 2, it's going to be very similar. This time it's with the segment SU. So now SU can move parallel to where it is. And look at what happens to angle X, all else being equal. You see that? All I did was I moved SU parallel to where it was. Left everything else the same, and look what happens to the size of X. So statement 2 isn't sufficient on its own either, because look how X can change even though I'm following the rule that statement 2 gave me. I mean, all that rule requires is that SU doesn't change its angle, essentially the angle SUT and the angle UST stay the same. So as long as you're moving SU in parallel to where it was, you're fine. You're following the rule, and yet the size of x changes significantly. You're right, it's not accurately drawn. We can see, I think it's probably easiest to see, probably here it's easiest to see that ut does not look equal to st at all. Probably easiest to see it here. Right? St looks longer than ut, but I don't care about how it looks. I just care about what do I know. Right? I know that this line can move there, 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 as long as it's parallel to where it was. And then look at what they're asking about. They're asking about x, but x is always going to be a different x because q stays where it is. So now qs is this, now qs is this, and so on. Yes, I find that in geometry data sufficiency, given that we have only 2 minutes per question, if I can visualize the degrees of freedom, as I call it, or again, the other side of the coin is, what does this statement constrain, like what are the constraints that are provided by this statement? In what way does the information in the statement force x to be a single value versus allows x to be more than one value? As long as the statement allows for multiple values of what they're asking for, then it's not sufficient. And to me, that's the quickest and easiest way to prove insufficiency if you're capable of visualizing this stuff in your head. And if you're not capable, then I have some great news for you. I didn't used to be capable either, but I practiced it and I got capable. I was absolutely terrible at geometry in middle school. I was the worst in my class. Couldn't visualize anything. But I practiced and I got better. Statement 1 gives us the following constraint. Yes, we can move segment SQ, but only in parallel to where it was. What about SU? Whatever we want. Statement 2 is the opposite. Statement 2 says you can move SU wherever you want as long as it's parallel. That's the constraint. SU has to be parallel to where it is. But no constraint for QS. With QS, you can do whatever you want. It's only if we combine the statements that now we are only able to move SU and SQ parallel to where they are, both of them. So they have to remain parallel. What could that look like? That's what I have here, right? So I have SQ and SU. This is what the original diagram looks like. If I move SQ parallel to where it was, SU also has to move with it parallel to where it was. You see that? And look at what happens to the value of x as I do this. As I shift them both together, and look at that. What happens to x? As long as SU is parallel to where it was, and SQ is also parallel to where it was, do you see how x stays the same in all of these cases? So if I'm at the test center, at this point I probably say, look, I don't have the time and or I don't have the skill necessary to calculate the value of x, but the fact that these statements constrain x to a single value gives me great confidence that if I did have the time and or the skill, I could find the value of x, because there's a singular value that these statements allow for. Now, since we are not at the test center, I'll take you through how to actually calculate the value of x. But I think the right strategy at the test center is to say, look, I have neither the time nor the skill, or maybe I have the skill but not the time, or vice versa, but I don't think that it's appropriate for most people to actually go ahead and compute x, as long as you can convince yourself that, yeah, if both of these statements are in play, and they're constricting x to a singular value, which we can kind of see if we visualize it in our heads, then one would be able to compute x if one wanted to. And the beauty of data sufficiency is we don't actually have to compute it. We just need to be confident that someone could compute it if someone wanted to. Now, if I actually did want to compute it, here's how I would think about it. I don't have that much information about actual angle sizes. The only information I have about actual angle sizes is I have the 90 degree here. And I know that the sum of the angles in each triangle is 180. So the big triangle, RPT, has a sum of 180. The small triangle, RQS, has a sum of 180, and the small triangle TSU has a sum of 180. And then the last thing I know in terms of actual values of degrees is that this degree here, this RST, is a straight line, and therefore that's also 180. So those are all of the pieces of information that I have. But then with the statements, I also know that this angle here, which I will call A, is equal to this angle, which we'll also call A. So A equals A, and we'll also say this is B, and this is B. So B equals B and A equals A. So we know that thanks to the statements. Now we can also say that angle R plus angle T are 90 because P is 90, angle P is 90, and the sum of the angles in the big triangle is 180. So I'm just going to keep calling them R and T. So angle R plus angle T together is 90. So I know that. But I also know that the total number, or the total angles in the two small triangles, QRS and SUT, is total of 360. So we have 2A plus 2B plus R plus T is 360. That's all of the angles combined from the two small triangles, from SRQ and STU, altogether is 360. But since we know that R plus T is 90, we can infer that 2A plus 2B is 270, which means A plus B is 135. I just reduced the equation by a factor of 2. And now I can find x because, again, we know that RST is a straight line. B plus x plus A is 180, but B plus A is 135, so x must be 45, the remaining 45 degrees. And I think most people would agree with me that it's just not appropriate to go through all of that in the middle of the GMAT. The right strategy for this question on the GMAT, and probably the strategy that they intended, they, the creators of the test, they wrote this question. And their intent was to test our quantitative reasoning, not to test our knowledge of geometry, not to test our math or our algebra, just our quantitative reasoning. So if you keep that in mind, what are they really testing here? What did they have? What did they have planned for the perfect test taker? The one who's going to get 800. How are they expecting that person to solve this in under 2 minutes? And I think that's the way, is to visualize what are the constraints that each statement gives us, what are the constraints that they give us when you combine them, and within those constraints, can we visualize multiple values for x? Can we visualize that angle changing, or do the constraints fix the angle at a certain number? And if we can see that, then maybe we don't even need pen and paper for that question.
But there'll be just too many scribbles on my yellow pad.
What if you do it with your hands? I've done this at the test center, by the way. It's allowed. They won't knock you for using your hands at the desk, but you can use your hands, do an angle, and then say, okay, I'm moving each hand. I'm moving them both in the same direction. The point where they touch each other can't change. They have to continue to touch each other. That's part of the constraint of the question, right? Because point S is point S. It's a singular point where the two segments meet. And if I'm moving both hands parallel to where they are, I couldn't possibly change the angle between them. The only way I can change the angle between them is if I move one of the segments not in parallel to where it was. That's the only way that x would change.
Yeah, but why can't you do that with what you were doing right now with your hand? I mean,
well, the statements, when you combine the statements, you can't. You're not allowed to, because think about what happens to the sides of the triangle. I mean, if each of these hands is a side of a separate triangle, if I move this hand like that, well, now it's no longer an isosceles. Like, they're telling you that it's an isosceles triangle, meaning the two sides that make up that triangle have to remain equal to one another. So the only way I can move this side is like this. Otherwise, they will no longer be equal to one another. So I can only move it in parallel. And the same goes for this hand. That means that the angle between them is fixed. I can't do that. The statements don't allow for it. So I actually would recommend to all of you, go into the official guide, scan it for data sufficiency geometry questions. It's very easy to find them because they'll have a diagram usually. and it's in the data sufficiency part of the book, obviously, and practice visualizing what does each statement allow for, and could that lead to different answers to the question. Hey, I'm just going to interrupt my own video for a moment here. If you're finding value in this video, please let me know in the comments below, and give this video a thumbs up. It really motivates me to keep uploading a new video every day. Alright, back to the video. Okay. Does anyone notice anything interesting here with the two statements? Let's just start with those.
Both are same.
Good. Yes, these statements are giving us inferentially equivalent information. Right? If we know that QPR is 30, if this is 30, we can infer that the sum of the other two angles in that triangle is 150. How can we make that inference? Because we know that the sum of all angles in a triangle is 180. So statement 1 implies statement 2, and the same goes in the other direction. If we know that the sum of angle Q and angle QRP is 150, we can infer on our own that QPR is 30. We don't need a statement to give that to us. So does anyone remember from the second section of the book, which answer choices can we eliminate without even reading the question?
A, B, C.
Fantastic. Good. So we can eliminate A, B, and C without even reading the question. This is either going to be D or E, and that's what we need to figure out. Now there's a rule that I think is being tested in this question. It's called the exterior angle rule. And what the exterior angle rule says is that this angle here is the sum of these two. And I'm going to give you the reasoning behind that, because we don't like to just memorize rules. This outside angle, what's known as the exterior angle, we know that it completes this angle in here to 180. Right? Together they have to be 180 because they're on the same line. But isn't it also true that these two angles, these two interior angles, let's call them A and B, isn't it true that they also complete this one to 180? So on the one hand, the exterior angle completes it to 180. On the other hand, these two, A and B, complete it to 180. Well, then the exterior must be the same as A and B. Because in both cases, they complete some guy, let's call this X. The exterior angle completes X to 180, and A and B also complete X to 180. So if two different things complete X to 180, then those two different things must be equal to one another. So that's the reasoning behind the exterior angle rule. And I think that's what they're testing here, because they're asking us the difference between PRS and PQR. So PRS is here. That's an exterior angle to that top triangle, to QPR. And they're asking what's the difference between that exterior angle and PQR, which is that teeny angle at the top there. Well, the difference between them will be this angle here, because we know that exterior angle is the sum of those little tiny angles, PQR and QPR. Let's use some letters to make this clearer. Let's call this A, B, and we'll call this X. They're asking us what's X minus A, but we know that A plus B is X because of the exterior angle rule. So if they're asking what's X minus A, they might as well just ask what's B. That's really what the question is asking. So we can rephrase the question to what is B, and each statement on its own gives us the answer. So the correct answer is D. So I think before we attempt this question, we should briefly talk about what is a function. What does a function do? I like to think of a function as a black box that receives some kind of input and then does whatever it is that it does and spits out the output. And that black box will always do the same thing to whichever input you send in. So just to explain that further, if we go and look at answer choice A, what does that function do? It takes the input, x, and it subtracts it from 1, and then it spits out the result. So if x was 5, it would spit out -4. If x was a quarter, it would spit out 3/4. Whatever x is, you subtract it from 1, spit it out. What does answer choice B do? Well, that function would square the input, and once it squared it, it would subtract it from 1. So if you throw in 4, it would spit out -15. Right? It squares the 4 and then subtracts it from 1. Answer choice C has a more complicated function. It squares the input, and then it subtracts from that, what? The square of 1 minus the input. It's a pretty sophisticated function. It does quite a lot of work, and then spits out the output, and so on. So that's what a function does, and each function is unique, and it does a different thing to the input. What this question is asking is, they want us to find a function that would spit out exactly the same output regardless of whether you throw in a value or 1 minus that value. This function doesn't care. This function has a certain kind of symmetry when it comes to a value and 1 minus that value, and that has to work for all x. So regardless of the value of x, whatever it is, this is a pretty high order. We're looking for a function that no matter what input you send into it, will always give you the same output as it would if you sent in 1 minus that input, 1 minus that value. There's not a lot of functions in the world that would do that would give you the exact same output regardless of whether you sent in an input or 1 minus that input. And this has to work for any x, for any input. Not easy. As an example, we're looking for a function that wouldn't care whether you sent in 100 or -99. Either way, with 100 and with -99, also known as 1 minus 100, either way you'll get the same output. What kind of function would do that? Would give you the same exact output whether you sent in 100 or -99. Now remember, this is a 2-minute per question kind of test. And also remember that it's not a math test, it's a quantitative reasoning test. So we should be able to solve this ideally without pen and paper, just by kind of looking at the functions that we have here in the 5 answer choices and wonder which of those would offer that special kind of symmetry that would imply that it doesn't care whether you send in x or 1 minus x. Is there a function in these answer choices that says, hey, I'm going to spit out the same result when you send in x as when you send in 1 minus x. They're looking for a function that would work for all x, and Paulina observed that in answer choice E, it would actually be undefined for x equals 1. And that eliminates that answer choice. Well done. Does any of these answer choices pop out at any of you as a symmetrical answer choice? What I like about D is that we have multiplication there, and the order in multiplication doesn't matter. And thanks to the even exponents, it also doesn't matter which side of 0 we're on. So we have a symmetry around 0, thanks to the even exponents. We have a symmetry because of the multiplication, because the order doesn't matter. And we have x and 1 minus x, which gives us the symmetry that we were hoping for. So D is the correct answer, and the reason why C doesn't work is because the order in subtraction does matter. So there's a really important difference there between the subtraction. This is a conceptual difference between the operation of subtraction, which cares about the order, and the operation of multiplication, which doesn't care about the order. That's why D is good and C isn't. Now B, if you're clever enough to notice the special product, B has a very nice symmetry going on for 1 minus x and 1 plus x. You see that? But we're looking for a symmetry for x and 1 minus x. And answer choice A doesn't have any symmetry. So we're good. D. So what we would do in order to prove that D is the correct answer, I kind of picked it by process of elimination. I didn't really prove that it's right. I just didn't like all the other ones, and I really appreciated the symmetry in D. And I also know what the GMAT is out to test. So based on knowing what they like to test, it stands to reason that D is the correct answer, because they're trying to test quantitative reasoning. If we wanted to prove it algebraically, we would do the following. We would write out x squared times 1 minus x squared, just like that. So I'm copying the answer choice. And now I'm going to write it again, but this time, anytime I see x, I'm going to throw in a different input. I'm going to throw in 1 minus x, because that's the input. So it would be 1 minus x squared times 1 minus x squared. And our goal is to see whether these two are equivalent. Right? If I simplify this second one, would it just end up looking like the first one? Well, let's do it. So we have 1 minus x squared times, what's 1 minus x? So 1 minus 1 disappears, and minus negative x is just x. And then we have the square there. Is this the same as this? Yes, because the order doesn't matter. So now I've proved it algebraically. I don't think, though, that I would do that at the test center. I want to make sure that you're getting the right takeaway from this question, because remember, we don't care about the question itself. We want to see what we can learn from the question that we could apply in other questions. I think the important takeaway is to appreciate the symmetry in answer choice D. So let me repeat again why I say it's so symmetrical. I love the even exponents because they offer us that symmetry around 0. It doesn't matter which side of 0 it's on, it's going to lead to the same thing. And the multiplication gives us the symmetry of not caring about the order, which we didn't have in answer choice C, because subtraction does care about the order. I think that's really the most important takeaway that you can actually use in a variety of different GMAT questions. Like, I've seen it tested so much. This importance of, does order matter or does order not matter? Does the order matter in division? Like, is 3 divided by 7 the same as 7 divided by 3? The order matters. So that's another way to eliminate E. E is not symmetrical. You're trying to understand the difference between symmetry and no symmetry, right? So we're looking for some kind of symmetry between x and 1 minus x. Answer choice A doesn't have any symmetry between x and 1 minus x. Same goes for B. Again, B does have symmetry between 1 minus x and 1 plus x. There's a symmetry there, but not between x and 1 minus x. C almost works, except the order matters in subtraction, so it's not symmetrical. D is perfect, and E, order matters in division, so it's not symmetrical. I really think that's the concept that they were trying to test here. That's why the question was designed for that, not for people to start plugging in a bunch of algebra or smart numbers or anything like that. If you found this video useful, go to quantreasoning.com for a lot more where that came from. You should also click that like button and let me know in the comments below what you'd like me to make future videos about. And of course, if you haven't yet subscribed, go ahead and do that and click that bell below so you get notified about future videos. See you next time.